Okay, it's my pleasure to welcome everyone back to the final part of the final session of BBQ. And it's great that we can have Serge Rosenblum speaking about error-corrected operations on encoded bosonic qubits. I think it's a super exciting topic, and take it away.
Hello, everyone. Thank you, Josh. So first of all, let me thank the organizers for inviting me to this wonderful workshop. So I'm actually a new faculty at the Weizmann Institute of Science in Israel, but today I will talk about my previous work at Yale University in the lab of Robert Schoelkopf. So before I get started, I want to thank Phil Reinhold from the Schoelkopf Lab, who worked with me on the experimental side, and also Wenlong Ma from the Zhang group, who did most of the theoretical work. So if you'd like to read more about this research, I encourage you to look up these two articles here. Can you see my mouse?
I can't actually.
Oh, okay, well.
Oh, now I can. Sorry, my apologies.
Okay, all right. So, well, since most of us are devout groupies of bosonic qubits, myself included, I won't spend too much effort in trying to convince you why they're so great. But still, you know, for an intro slide, let's go ahead. So first of all, bosonic modes can reach superior lifetimes, more than a millisecond for superconducting cavities. And we also get this large redundant Hilbert space that is super useful for doing quantum error correction. And as a free bonus, we get a very simple noise structure in which photon loss is by far the most common error. But what's less often pointed out is that there's a very large disadvantage to bosonic qubits, which is that by driving the cavity with this microwave pin here, all we can do is displace the fields. And this is, of course, far from what we need to achieve universal quantum control over the bosonic qubit. So maybe the most important challenge that is faced by bosonic qubits is that they require coupling to a nonlinear element, which is, of course, a completely different beast. And I was very happy to learn that Steve Gervin is kept awake at night because of that problem. And so I'm happy to see that I'm not the only one. And yeah, so let's see why it's really such a problem. So in our most basic experimental setup, we take this beautiful high Q resonator, and we attach to it this ugly, noisy, nonlinear element. So in our experiment, we use a transmon ancilla, which gives us the ability to encode, decode, and also to control our logical qubits. So there's something I want to emphasize here. The problem is not only that the ancilla has more than an order of magnitude worse decoherence in the cavity. So in our case, the cavity lives, a single photon lives for a millisecond, but the transmon only for 50 microseconds. The main problem is actually that the ancilla changes the noise structure of the cavity completely. So photon loss is very often not the dominant error, but we get also all kinds of different stuff now. So if the transmon were to introduce displacements or photon loss, we could deal with that using error correction, but that's just not the case. And usually the errors that we get are uncorrectable. And I also want to point out that this is not something that's exclusive to bosonic qubits. It also affects other architectures in some different sense. So it's, of course, easy to get universal control of physical qubits, but it's much harder to do that for logical qubits. For example, the Easton-Knill theorem proves that fault-tolerant transversal gates are not universal under some very general set of assumptions. So many architectures, such as the service code or concatenated codes, also involve ancilla qubits to reach this universal control. But here too, errors from imperfect ancilla qubits can propagate to the logical qubit and cause uncorrectable errors. Right? So in this non-fault tolerant case, a single error in the ancilla propagates into two errors in the logical qubit, which may not be correctable. And generally, this means that what you have to do is you have to also encode the ancilla itself. So it seems that there is a trade-off here where we must pay a huge price in complexity and hardware to make our operations fault tolerant. Now, to have a better understanding of what this means, let's have a look at some of the recent breakthroughs in bosonic quantum computing. So in this, on the left here, you see a picture from the first demonstration of quantum error correction at the break-even point, a work by Ofek and Petrenko. And in fact, in that experiment, the factor that limited them and stopped them from going beyond break-even is in fact ancilla decoherence during the parity measurement. So typically, the measurement of parity takes about a microsecond, and the coherence time of the transmon is about 100 microseconds. And so you get this 1% error probability in the ancilla, which then propagates to the logical qubit. And similarly, when you try to apply gates to your logical qubits, you also get this 1% error probability. So this was nicely phrased by Liang in his opening lecture, where he called this the 1% curse for bosonic quantum computing. So it turns out that there is a method that we can use to prevent ancilla errors from propagating to the logical qubit, and at the same time, to fully maintain the ability to control the cavity. So in a previous paper, we showed how we can do parity measurements in a fault-tolerant way. And in this work, I will show you an even more complex task, which is to apply gates to the to the logical qubit without being limited by ancilla decoherence. So to understand the key idea here, let's consider the following general picture. So suppose we have a logical qubit and an ancilla, which interact with one another. And now we want to apply gates to the logical qubit by manipulating the ancilla. So let's say that we start with the ancilla in state A, and then we carry it along some path to a fixed final ancilla state B. And thanks to the interaction, this will also affect a certain operation onto the logical qubit. But if the ancilla suffered some error during this evolution, it could have reached this final state through a different path. And this would result in different gates being applied to the logical qubit. And in general, this means that an ancilla error has propagated to become an uncorrectable logical error. Now, this way of looking at this should look vaguely familiar. So, of course, if you go climbing on a frictionless mountain, you know that it doesn't matter what path you take to the summit. The number of calories you will have burned does not depend on the trajectory you take. And the energy difference, which is of course the line integral along the path here of the force, it's fixed entirely by the ending and starting points. Or equivalently, you could say that any closed loop that gets you back to your original position gives you a total of 0 energy. And this is, of course, a general property of a curl-free vector. So we are going to use an analogous concept for achieving error-corrected gates on an ancilla, on logical qubits, which we call path independence. So roughly speaking, a gate is path independent if its operation on the logical qubit is independent of the trajectory of the ancilla. A bit more formally, we can write down the propagator, GP. So this GP is a propagator on the system for a total of P errors on the ancilla. So to give an example, G0 would be the error-free propagator on the system, and G1 would be an error-free propagation until a certain time, followed by an ancilla error, and then for the rest, you again have this error-free propagation, and you can go on. So formally, we would say that the gate is path independent to nth order in the error J if, given that the ancilla starts in A and ends up in B, all propagators with fewer than n errors give you still a fixed unitary on the logical qubit. So now, what are the criteria for achieving such a path-independent gate? So the first criterion is that the error-free evolution from any state in the ancilla to any other state should be given by a unitary operation on the logical qubit. And secondly, the unitaries have to satisfy the following chain rule. So for every triplet of ancilla states k, m, and l, ukm times uml should equal ukl. For example, on this picture here, if you take the ancilla directly from A to B, that would affect the operation UBA on the logical qubit. But if instead you go through the state E, you have UEA times UBE, which should equal UBA by this chain rule. Equivalently, you could say that any closed loop in ancilla state space should give you the identity operation. And this is, of course, analogous to this zero in a closed path that we saw earlier. Now, it turns out that if your path independence criteria are met, the gate is going to be protected against ancilla dephasing errors to an infinite order. So this is pretty remarkable, at least when I first learned about that. So let's see how this magic happens. So of course, dephasing means that the environment projects you, or rather projects the ancilla to some eigenstate. Now, suppose you want to bring the ancilla from A to B, but the environment measures that your ancilla in the middle of the gate is in the state E. But that's okay, because the projection operator EE acts trivially on the ancilla space, and UBE times UEA equals UBA by the chain rule. So you end up with the same gate UBA, even in the presence of this projection. And you can convince yourself that no matter how many times you apply this kind of projection, no matter to what state, the evolution from A to B always corresponds to the same logical operation. Now, going back to our classical analogy, you could, of course, say that there is no particular reason that if there's an error, you would reach the correct final location. Instead, you could just end up in the wrong place altogether. But you could argue that if you know where you ended up, you can then use that information to still calculate how many calories you've burned. And the same is true in our case. So since the ancilla does not carry any logical information, we can just measure it at the end of the gate. And this measurement will tell us unequivocally which unitary was applied. And this turns out to be particularly useful to tackle relaxation errors. So suppose that instead of going from A to B, the relaxation of the ancilla collapses us to some other state E. Now, if we measure the ancilla and we see that it's in E, we can again exactly know what operation was applied to the logical qubits. And in this case, this is just the identity. And we can then reset the ancilla and just try again until we succeed. And I'll just note here that it's not so trivial to remove the back action of this relaxation operator onto the logical qubits, but it can be done, and this is what we did in our experiments. So in our demonstration of this, we are going to use the Kitten code, and we like that code because its Hilbert space is truncated, and so it's easier to control. Now, in the Kitten code, to remind those of you who might have forgotten, the logical 1 is the 2-photon Fock state, and the logical 0 is 0 plus 4. So we have a well-defined parity here. And so if a photon is lost from the cavity, we can detect this error by just measuring the parity of the photon number. And it turns out that we can do more than just detect the error, and that's because all states on this Bloch sphere have the same average photon number, which is 2. So the photon that leaves your cavity carries no information about your location on the Bloch sphere, and so you can still recover from this error, and you can just get your original qubit back. So this is actually error correctable, not just error detectable. Now, in our experiment, the transmon is dispersively coupled to the ancilla, and we will use the photon number splitting to apply our logical gates. So here you can see a transmon spectroscopy experiment for up to 4 photons in the cavity, and you can clearly see this dispersive shift by chi, which is about 1 megahertz in our experiments. And we're going to use this spectral separation to independently address the ancilla for each one of those Fock states. So the idea here is to apply a slow selective pulse that brings the ancilla from G to E, but with a different phase for each Fock state component. And this way we can impart arbitrary phases to each number of photons in the cavity. Right, so we have basically complete control over the phases by doing that. Now, this very powerful operation is called the snap gate, which stands for selective number-dependent arbitrary phase gate. And we can use that operation to apply logical gates to our Kitten qubit. So remember that our logical 1 is a 2-photon Fock state, and the logical 0 is 0 plus 4. So if we apply a 0 phase for the 0 and 4 Fock state components, but we apply an arbitrary phase theta to the logical 1, to the 2-photons Fock state component, then this will perform a logical 0 rotation around the Bloch sphere. So let's do an experiment where we vary the phase that we apply to the 2-photon Fock state, and then we will measure the Wigner function of the cavity. So this here is data, and you can see that indeed by varying the phase that we apply to 2, we go around the equator of the Bloch sphere. So for simplicity in the rest of the talk, let's just focus on one rotation by pi over 2. And all you have to remember is that it takes our initial state, which is this Kitten state, to this happy clown face. So now, in general, of course, during the logical gate, the ancilla and the logical qubit become entangled. So what I'm going to show you is how a path-independent version of the snap gate will enable us to protect the logical qubit against forward propagation of ancilla errors. Now, to get started, our first task is going to be to distinguish between the 3 possible outcomes. So we have no error, or we have an ancilla relaxation, or an ancilla dephasing event. So it makes sense to use 3 levels instead of 2. And instead of doing the snap gate between G and E, we're going to drive the ancilla from G to F directly without ever populating E. And after the snap gate, we, of course, measure the ancilla, and this will tell us which event happened after the snap gate. Sorry, which event happened during the snap gate. So if there's no error at all, then we will measure F, and indeed you will see that the logical gate will be successful. But if we measure that our ancilla is in E, that means that there must have been some relaxation events during the gate. But that is still OK, because you can only get to E by passing through F. So the snap gate was applied, and the gate was still successful. Finally, if you measure G, that means you have a dephasing event. And you see that in this case, the trajectory was not completed. You just stay in G. But that's not too bad, because you can see the logical qubit still survives. So we can repeat the process and reapply the gate. And what's important here is to note that if we measure the ancilla, in every outcome, the purity of the logical state is maintained. And this should ring a bell. Right? This is exactly, well, this gate was exactly designed to meet the path independence requirements. So to see why that's the case, let's inspect the graph of possible ancilla transitions. So the green arrow here is the snap operation, which applies the operation S theta. And the transition from F to G is just the Hermitian conjugate, so it applies the operation S minus theta. So you can see that any closed loop from G to F gives you S theta and then S minus theta, so you get the identity. And this is, of course, a fundamental requirement for path independence. And this still holds no matter how many times the environment projects you onto one of the ancilla eigenstates. Right? Suppose you have this S theta, and then the environment projects you to F, which is the identity operation on the logical qubits. And then you go back. Well, this still gives you the identity, so we're good. And if we measure E, there's only one trajectory that can get us there, and that's a successful snap gate followed by relaxation. Okay, so
5 plus 5 left.
Sorry?
You have 5 minutes plus 5 minutes left.
Oh, okay. So I will get to the data then. So what I want to point out here is that no matter which trajectory you take here, we know exactly what unitary we get. All right. So before getting to the data, I just have to tell you how we perform the snap gate from G to F without going to E. And we do that by using the 2-photon Raman transition. We have one strong tone detuned from GE and many weak tones detuned from EF that each drive a different Fock state component. So in this first experiment, you can see that when we apply this Raman GF snap and we measure the ancilla and then measure the Wigner function of the cavity, we see that we have a pure logical qubit as we expected. And indeed, if we obtain dephasing, we know that we just have to reapply the gates and try again. And you can see that this matches with simulations very nicely. I will have to skip this slide. So now let's put all of these ingredients together and see how well our error-corrected gate works. So a good way to characterize our gates is to use interleaved randomized benchmarking. So what it means is that we sandwich our logical gate in between random Clifford gates that we generate using optimal control methods. And then we measure the probability that after n such cycles, we get to the correct logical state. And by looking at how quickly the fidelity goes down with the number of cycles, we can then deduce the error of our gate. So what you'll see is that the non-error corrected gate, so just a snap gate, gives you a 4.6% infidelity. Whereas if we use ancilla measurements and then feedback, we get to a 2.4% infidelity. So we have this factor of 2 improvement. And I'll just mention that most of what's going wrong here is just the fact that you still can lose photons in the cavity. But that we know how to deal with by just doing quantum error correction. Right, so the dominant error now is photon loss and not forward propagation by the ancilla. And now in the final piece of data, I want to show you explicitly how the suppression of errors from the ancilla to the logical qubit works. So I don't have time to explain it, but we are able to increase artificially the ancilla relaxation errors as well as the ancilla dephasing errors. And you can see that when we use the non-error corrected snap gate, well, the logical infidelity follows exactly the probability of an ancilla error. So every time you have an error in your ancilla, this becomes a logical error. However, when we use the error corrected logical gate, which satisfies path independence and feedback, etc., you get this very large suppression of forward propagation. Right? So every ancilla error has now only a 1 in 6% chance to propagate in the case of relaxation errors, and a 1 in 4 chance in the case of dephasing errors. In the outlook, I'll just mention that you can, in principle, increase the protection against more errors by using more and more levels in the ancilla qubits. All right, so with this, let me thank my colleagues again at Yale, and I will be happy to answer any questions that you may have.
Thank you so much, Serge, for the great talk. I really enjoyed it. Oh, and we've already got some questions here.
Ah, great.
So let's see. So can the ancilla measurement, I guess, be used to determine the gate and feedback be done autonomously? For instance, using controlled gates from the ancilla to the cavity?
So if the question is, can we replace some of that measurement and feedback by using autonomous method? The answer is probably yes. We just haven't done that. For example, you can think of a scheme in which when there is a relaxation error, you have some pump that comes in and immediately pumps you back to F.
Right.
Okay, so you can replace this measurement and feedback by this procedure.
Yeah, that would be pretty cool. The second question we have is, when you do the GF snap operation, are you not doing a 2π rotation on the G2 F2? And so that's the first part. Why does a successful gate lead to the ancilla being in the F state and not the G state?
Right. So to answer the first question, so the 2π gates, the pi phase that you get is only if you do a full Rabi oscillation, right? But we don't do a full Rabi oscillation. We just go from the ground state from G to F, okay? And if you change the drive phase with which you do that, then you will apply a different phase to the logical qubit. So if you were to continue that gate, if you would apply it twice as long, you would get the pi phase. Yes.
Okay.
And the second question, please remind me.
Why does a successful gate lead to the ancilla being in the F state and not G?
I think this answered both questions, right?
Right. Yeah. So we just had another one, which is, would the scheme benefit from using a biased noise ancilla? So, just changing the ancilla.
Yes, and maybe I just want to add one more thing to the last question.
Okay.
So I think what the person had in mind is that this is a geometric gate, and so if you want to think about this as a geometric gate, you could go up with an arbitrary phase and then go down with a fixed phase for all photon states, and then you would end up in G, and you would still have different phases for all photon Fock states. Now, regarding a biased qubit, yes, that would definitely be helpful. Well, it would be helpful if one of the errors was reduced, not if the other one was increased,
Yeah.
of course. Yeah.
Okay.
I'll just say that what I just said about this autonomous error correction, right? So if you have this pump that brings you from E to F all the time, this would be a biased gate. Sorry, a biased ancilla, because it would eliminate relaxation errors.
Right.
Basically.
So I had a question about the last slide. I think I just maybe didn't quite catch what was going on. So this is where you're studying that, was it this slide? Yeah. So the ancilla relaxation rate you can kind of control. And so is it the case that the error that Liang was talking about, the curse of the 1%, is that the point on the left-hand side of the axis? Is that?
Oh yes. So the 1% would be the leftmost point here, exactly. Right. Okay. This is a natural relaxation and dephasing errors that we have.
Right. And relative to that, you've seen like I guess it's not on a scale, but what's the relative reduction in that at that point?
Right. So at that point, we would have a factor of 2 reduction.
Okay.
And the main limitation, except photon loss, which is benign, would be readout induced errors. Okay. This is why it's only a factor of 2 and not more.
I see.
But as we increase the ancilla errors, these parasitic effects become negligible, and you can clearly see the effect of our procedure.
Okay. And then there's hope to improve readout independent of this. So.
Sorry?
Yeah. Well, you said that the remaining errors were due to readout, and there's some hope that that can be fixed. So it's not really.
Yes, absolutely. There are things you could do.
Yeah. All right. Let's see. Any other questions? No. Okay. Well, let's thank Serge again, and you can send him more questions in Slack or on the chat here. And yeah, we appreciate you taking your time to chat to us.
Likewise.